Welcome to chemistry. In this presentation, we will explore one of the most fundamental skills in chemistry, determining empirical and molecular formulas from experimental data. We will start with the core definitions, then dive into percent composition, learn the five-step algorithm for finding the empirical formula, and finally unlock the relationship between empirical and molecular formulas through combustion analysis. By the end, you will be able to look at any unknown compound and figure out exactly what it is. Here is our roadmap. We will begin with percent composition, how chemists turn raw mass data into a percentage breakdown of each element in a compound. From there, we will define the empirical formula, the simplest whole number ratio of atoms in a compound, and walk through a five-step algorithm to determine it from any dataset. Next, we will introduce the molecular formula, the actual count of atoms in one molecule, and show how it relates to the empirical formula through a single ratio, the integer multiple n. Finally, we will study combustion analysis, the experimental technique that lets chemists figure out the formula of an entirely unknown compound, and we will wrap up with 5 quiz questions and 5 worked problems to test what you have learned. A chemical formula is a shorthand notation that tells us exactly which elements are in a compound and in what proportion. The image on the right shows how atoms, the colored spheres, bond together to form molecules, and how each molecule can be described by a small string of element symbols and numbers. For example, the formula H2O tells you that each water molecule contains 2 hydrogen atoms and 1 oxygen atom. The formula C6H12O6 describes glucose, with 6 carbons, 12 hydrogens, and 6 oxygens. Subscripts, the small numbers written below the line, give the count of each atom. The absence of a subscript means one atom of that element. Every formula you will ever meet is built from this simple idea: element symbols plus integer subscripts. Percent composition is the percentage by mass of each element in a compound. It is calculated by dividing the total mass of one element in one formula unit by the molar mass of the entire compound, then multiplying by 100%. The general formula is shown on the slide. Percent of element equals mass of that element divided by molar mass of compound times 100. For example, in 1 mole of water, 18 grams total, there are 2 grams of hydrogen and 16 grams of oxygen. The percent of hydrogen is 2 over 18 times 100, or about 11%. The percent of oxygen is 16 over 18, or about 89%. Percent composition is the bridge between the formula of a compound and the raw mass data that chemists measure in the laboratory. Let us apply percent composition to a real molecule, glucose, with the formula C6H12O6. Glucose has a molar mass of 180 grams per mole. Inside that 180 grams, there are 72 grams of carbon, 12 grams of hydrogen, and 96 grams of oxygen. The image on the right shows this idea visually, the relative mass that each element contributes to the whole molecule. Carbon contributes 72 divided by 180, which is exactly 40%. Hydrogen contributes 12 over 180, or about 6.7%. And oxygen contributes 96 over 180, which is about 53.3%. Notice that the percentages always add up to 100%. Every atom in the molecule is accounted for. This is a useful sanity check on every percent composition problem you solve. The empirical formula of a compound is the simplest whole number ratio of atoms in that compound. It tells you the relative number of each kind of atom, but it does not necessarily give the actual count in a single molecule. For example, the empirical formula of glucose is CH2O, because the ratio of carbons to hydrogens to oxygens in glucose is 1 to 2 to 1. The actual molecular formula, C6H12O6, is 6 times the empirical formula. Some compounds happen to have an empirical formula identical to their molecular formula. Water, H2O, and carbon dioxide, CO2, are good examples. But in many cases, the molecular formula is a whole number multiple of the empirical formula. The empirical formula is also called the simplest formula for this reason. It captures the chemical identity of the compound at the simplest level. Here is the 5-step algorithm for finding the empirical formula of an unknown compound from mass or percent data. Step 1. If you are given percent composition, assume a 100-gram sample. This converts percentages directly into grams. Step 2. Convert the mass of each element into moles by dividing the mass by that element's molar mass from the periodic table. Step 3. Divide every mole value by the smallest mole value among them. This gives the simplest ratio of atoms. Step 4. If any ratio is not a whole number, multiply all ratios by a small integer, 2, 3, or 4, until every ratio rounds to a whole number. Step 5. Write the empirical formula using these whole number subscripts. Memorize these 5 steps. Every empirical formula problem, no matter how it is worded, comes down to applying them in order. Let us apply the 5-step algorithm to a worked example. A 2.32-gram sample of an unknown compound contains 1.2 grams of carbon, 0.204 grams of hydrogen, and the rest is oxygen. Find the empirical formula. Step 1. Mass of oxygen. Total minus carbon minus hydrogen gives 0.916 grams of oxygen. Step 2. Convert each mass to moles. Carbon, 1.2 divided by 12 equals 0.100 moles. Hydrogen, 0.204 divided by 1 equals 0.204 moles. Oxygen, 0.916 divided by 16 equals 0.0573 moles. Step 3. Divide by the smallest, which is carbon. The ratio is 1 for carbon, 2.04 for hydrogen, and 0.573 for oxygen. Step 4. Multiply all ratios by 2 to clear the half. The ratio becomes 2 to 4.08 to 1.146, which rounds to 2 to 4 to 1. Step 5. The empirical formula is C2H4O1, or simply C2H4O. This is the empirical formula of acetic acid, the compound that gives vinegar its sour taste. The molecular formula of a compound is the actual whole number count of atoms of each element in a single molecule of the substance. It is always a whole number multiple of the empirical formula, never smaller, never with fractional subscripts. For example, hydrogen peroxide has the empirical formula HO with a 1-to-1 ratio of hydrogen to oxygen, but its molecular formula is H2O2 with 2 atoms of each. The multiple N here is 2. Glucose has the empirical formula CH2O and the molecular formula C6H12O6, which is 6 times the empirical formula, so N is 6. In every case, the molecular formula is a positive integer multiple of the empirical formula, and the integer N is the same for every element in the compound. Let us compare the empirical and molecular formulas side by side using 3 well-known compounds. Hydrogen peroxide. The empirical formula is HO, 1 hydrogen, 1 oxygen, the simplest whole number ratio. The molecular formula is H2O2, actually 2 of each in 1 molecule. The multiple N is 2. Glucose. The empirical formula is CH2O, 1 carbon, 2 hydrogens, 1 oxygen. The molecular formula is C6H12O6. The multiple N is 6. Benzene. The empirical formula is CH, 1 carbon, 1 hydrogen. The molecular formula is C6H6. The multiple N is 6 again. Notice that the molecular formula always has the same ratio of atoms as the empirical formula, just multiplied by a positive integer. And the integer can never be less than 1. If the empirical and molecular formulas are identical, then N equals 1. The connection between the empirical formula and the molecular formula is a single integer N, found by dividing the molar mass of the molecule by the empirical formula mass. The empirical formula mass is the sum of the atomic masses of all atoms in the empirical formula. For example, for CH2O, that is 12 plus 2 plus 16, or 30 grams per mole. The molar mass is the actual mass of 1 mole of the molecular compound, typically measured by mass spectrometry or determined from colligative properties such as freezing point depression or osmotic pressure. Once you have both, divide. For glucose, the molar mass is 180 grams per mole, and the empirical formula mass is 30. So N equals 180 divided by 30, which is 6. That is why glucose is 6 times its empirical formula. The whole number answer is the magic number that converts the empirical formula into the true molecular formula. Combustion analysis is the standard experimental technique for finding the empirical formula of an unknown compound containing carbon and hydrogen. A weighed sample is burned in excess pure oxygen. Carbon becomes carbon dioxide, which is collected and weighed. Hydrogen becomes water, which is also collected and weighed. From the carbon dioxide mass, we calculate the mass of carbon in the original sample. From the water mass, we calculate the mass of hydrogen. The mass of any other element, like oxygen or nitrogen, is found by subtracting carbon and hydrogen from the original sample mass. The image on the right shows the schematic of a combustion train. Sample in the furnace, oxygen stream, and the absorption tubes that trap carbon dioxide and water. Once we have all the masses, we apply the 5-step algorithm to convert them into the empirical formula. If the molar mass is also known, we can find the molecular formula. Here is the step-by-step workflow for analyzing combustion data. Step 1. Record the masses. You are given the mass of the original sample, the mass of carbon dioxide produced, and the mass of water produced. Step 2. Find the mass of carbon. Multiply the mass of carbon dioxide by the ratio 12/44, which is the ratio of carbon's atomic mass to the molar mass of carbon dioxide. This gives you the mass of carbon in the original sample. Step 3. Find the mass of hydrogen. Multiply the mass of water by the ratio 2/18, the ratio of hydrogen's atomic mass in water to the molar mass of water. This gives you the mass of hydrogen. Step 4. Find the mass of any other element, usually oxygen, by subtracting the masses of carbon and hydrogen from the original sample mass. Step 5. Apply the 5-step algorithm. Convert each mass to moles, divide by the smallest, multiply to whole numbers, and write the empirical formula. If the molar mass is also given, divide it by the empirical formula mass to get N, and multiply the subscripts by N to get the molecular formula. Quiz time. Question 1. A compound is found to contain 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Which of the following is its empirical formula? Option A, CHO. Option B, C2H4O2. Option C, CH2O. Option D, C2H6O. Take a moment to work this out. When you have your answer, the correct option and a full explanation will appear on the slide. Question 2. The empirical formula of a compound is CH2O, and its molar mass is 180 grams per mole. What is its molecular formula? Option A, CH2O. Option B, C2H4O2. Option C, C3H6O3. Option D, C6H12O6. Work it out. The empirical formula mass is 30 grams per mole, so N is 180 divided by 30, and the answer will be revealed shortly. Question 3. A combustion analysis of an unknown compound produces 3.3 grams of carbon dioxide and 1.35 grams of water. The original sample mass was 2 grams. What is the empirical formula of the compound? Option A, CH2. Option B, CH3. Option C, CH4. Option D, C2H6. Hint: first, find the mass of carbon in the carbon dioxide, then the mass of hydrogen in the water. The remaining mass is also part of the compound, so the empirical formula will reflect that element too. The answer will appear shortly. Question 4. The empirical formula of a compound is NO2, and the molar mass is 92 grams per mole. What is the molecular formula? Option A, NO2. Option B, N2O4. Option C, N3O6. Option D, N4O8. Find the empirical formula mass first, then divide 92 by that number. The result is your multiple N, and that reveals the molecular formula. Question 5. The final quiz question. A sample of an unknown compound weighing 5.85 grams contains 1.2 grams of carbon, 0.204 grams of hydrogen, and 1.6 grams of nitrogen. The rest is oxygen. What is the empirical formula? Option A, CH4NO. Option B, C2H8N2O2. Option C, CH2NO. Option D, C3H12N3O3. This is a 4-element problem, so use the 5-step algorithm carefully. Find the oxygen mass first, then convert every mass to moles, divide by the smallest, and find the simplest whole number ratio. Problem 1. Find the empirical formula from a given mass composition. A 2.32 gram sample of an unknown compound contains 1.2 grams of carbon, 0.204 grams of hydrogen, and the rest is oxygen. Find the empirical formula. Step 1. Find the mass of oxygen. The total mass is 2.32 grams. Subtracting carbon and hydrogen gives 0.916 grams of oxygen. Step 2. Convert each mass to moles. Carbon, 1.2 divided by 12 equals 0.100 moles. Hydrogen, 0.204 divided by 1 equals 0.204 moles. Oxygen, 0.916 divided by 16 equals 0.0573 moles. Step 3. Divide by the smallest, which is carbon. The ratio is 1 for carbon, 2.04 for hydrogen, 0.573 for oxygen. Step 4. Multiply by 2 to clear the half. The ratio becomes 2, 4.08, 1.146, which rounds to 2, 4, 1. Step 5. The empirical formula is C2H4O, or simply C2H4O. This is the empirical formula of acetic acid. Problem 2. Find the empirical formula from percent composition. A compound is 40.0% carbon, 6.7% hydrogen, and 53.3% oxygen by mass.